This series of videos covers material in the book Mathematical Modeling and Computational Calculus that I wrote. There is a synopsis of the book online, and I'll provide a link in the description below. In the course, we analyze a wide range of physical systems using computational calculus. There are two big advantages to using computational calculus as opposed to traditional analytic calculus. First, the principles of computational calculus are very easy to learn, and we'll cover the basics in this video today. And second, computational calculus is very powerful and can be used to analyze a wide variety of physical systems, most of which are completely intractable using analytic calculus. There's also a link to the slides in this video series provided in the description below. So let's get started. After recording this video, I noticed that we seem to be progressing at an excruciatingly slow pace, and indeed we will continue for some time at a slow pace, trying not to leave anything out. So you might think that we'll never get anywhere. But in fact, we're going to cover what seems like most of classical physics in this course and a second course. So I'll give you a brief preview of each of the topics we're going to cover before we start. We'll start today with Newton's apple, the two-body problem in one dimension. Next is the two-body problem in two dimensions. We calculate orbits for satellites, the moon, and the Earth. The three-body problem, the Earth, a rocket, and the moon. We fly a rocket from the Earth to the moon, and then give it a little push to put it into orbit around the moon. In August of 2011, the U.S. launched the Juno space probe, which completed a 2-year orbit around the Sun, returned to Earth, and then Earth's gravity flung the probe toward Jupiter, where it will arrive in October 2016. We compute the trajectory. We spend a lot of time on electric circuit analysis, starting with the simplest circuits and working up to circuits with several components. The orbits and rocket trajectories were calculated for point masses. Rigid body dynamics treats objects as having 3, or in our case 2, dimensions, and models both position and orientation. So when a force acts on a rod, as shown, the rod's center of mass moves, and also the rod rotates about the center of mass. We model a bouncing ball hitting the ground. We analyze an auto suspension system reacting to a bumpy road. We spend some time on a 2D airplane simulator, modeling lift, thrust, drag, and gravity, and the airplane's angle of attack as it flies. Control is exercised by controlling the tail elevator, which produces a torque on the plane, and the graphs show an attempted pitch up, which caused the plane to stall. We model a 2D rocket with a thrust phase and control the thrust angle for guidance. We simulate a launch to orbit. Finally, we model a robot, starting with the circuit model for the electric motor and the dynamic model for the robot cart. The graph shows the result of using a PID controller to move the robot 1 meter. This completes the first course. The second course covers the material in the second book. The mathematics in the first course is Euler's method for computing the solutions to ordinary differential equations. It consists of making the substitution shown into a differential equation to get a computational equation which is then used to compute solutions. The second course uses the finite difference method to compute the solutions to partial differential equations. It is, just like Euler's method, based on the formula distance equals velocity times time. And despite the proliferation of characters, it is perfectly simple and intuitive once you're familiar with it. Trust me, I'll tell you if things get difficult. Everything has been easy so far, and it will remain so, but not forever. The model for heat transfer is Fourier's heat transfer law, which states that heat flows from hot to cold areas. It doesn't get any simpler than that. Note that we only have to compute the solutions. The one MATLAB feature beyond performing additions and multiplications that we use is the plot function, which does all the work in making the fancy graphs. There are several models for the wave equation. We derive it from the familiar force equals mass times acceleration. Again, MATLAB plot functions produce the great graphs. I said I'd tell you when things get difficult, and this is it. The problem is that when you squeeze an elastic object, it not only compresses in the direction you're squeezing, it bulges in the perpendicular direction. So Hooke's law, shown in 2D, is a matrix equation. Not only that, vectors are not adequate to the task of representing stress and strain, and tensors enter the picture. Now most of our effort is devoted to developing the model, and we break everything down step by step with nothing left out. The graphs show the effects of applying various tractions to a 2D elastic plate. The underlying physics for the Navier-Stokes equations is Newton's second law of motion and Newton's law of viscosity, which is equally simple. However, deriving the equations requires some effort. We'll leave it at that. The results are fantastic. The graphs show fluid flowing in a pipe, in a cavity, and over a backward step. Maxwell's four equations are easily derived from four simple experiments. And Maxwell's equations in differential form are the model for electromagnetic radiation, and the finite difference method can be applied right out of the box. We generate EM waves in 1 and 2 dimensions, and also cover Yi's algorithm, which is a modification of the finite difference method that has become the standard tool for analysis of electromagnetic radiation. The preview is complete. Now we begin. We start with what is probably the first calculus problem ever, and that is computing the position of an apple as it falls from a tree. Newton's solution to this problem and the associated problems of determining the orbits of the moon, the planets, and the earth marks the beginning of modern science and technology. So it's a good place to start. The first thing Newton did was discover or postulate there was a force pulling the apple toward the earth, and he named this force gravity. We're going to start by assuming that the force of gravity is constant, and we'll get to Newton's actual law later in this video. For now, we'll assume that the force of gravity acting on the apple is constant and equals F sub g. Newton also discovered the laws of motion. The operative law is the second law of motion, which is F equals m times a, or force equals mass times acceleration. So with gravity being the only force acting on the apple, we'll get to atmospheric drag in the next video, the acceleration of the apple is given by a equals the force of gravity divided by the mass of the apple. And if we plug in the numbers using Newton's formula, it comes out to be about minus 10 meters per second. So we'll use this value for the acceleration of the apple as it falls. So as the apple falls downward, its velocity increases by 10 meters per second every second that it falls, with the negative sign appearing because the velocity is downward. The table shows the velocity of the apple as it falls. The apple drops at time t equals 0, and its velocity at that instant is 0. After 1 second, its velocity is minus 10 meters per second. After 2 seconds, it is minus 20 meters per second. After 3 seconds, it is minus 30 meters per second. And after t seconds, the apple's velocity is minus 10 times t meters per second. Thus, the velocity of the apple is given by the velocity function v of t equals minus 10 times t. Our goal is to determine the position function p of t, that is, the position of the apple at any instant t as it falls. This is how we do it. We want to compute how far the apple falls in t seconds, and we'll limit the time interval of interest to from 0 to 10 seconds. We divide the time interval into subintervals and calculate how far the apple falls in each subinterval by assuming that the apple's velocity is constant over the subinterval and equals its velocity at the start of the subinterval. It's as simple as that. We'll illustrate by starting with 2 subintervals, each 5 seconds long. The first subinterval is from t equals 0 to t equals 5, and we estimate the distance the apple falls by multiplying its velocity at the start of the subinterval, v of 0, which is 0 meters per second, times the length of the subinterval, which is 5 seconds, to get 0 times 5, or 0 meters. So our estimate is that the apple doesn't fall at all for the first 5 seconds. We're off to a slow start. The second subinterval is from t equals 5 to t equals 10 seconds, and we estimate the distance the apple falls during this subinterval by multiplying its velocity at the start of the subinterval, v of 5, which is minus 50 meters per second, times the length of the subinterval, which is 5 seconds, or minus 50 times 5, which equals minus 250 meters. So now we're picking up some speed. To graph the apple's position as it falls, we need a starting point. So we'll assume its initial position is 500 meters. The apple falls at a constant velocity of 0 meters per second for the first subinterval and a constant velocity of minus 50 meters per second for the second subinterval. So the graph is piecewise linear, consisting of 2 straight line segments, one for each subinterval, as shown. Clearly, this approximation to the trajectory of a falling apple is not good, but it only gets better. This graph shows the trajectory computed using 5 subintervals of 2 seconds each. If we want to do much better than this, we'll need to automate the computations, so we turn our attention to that. We start with the velocity function, v of t, and we want to calculate the associated position function, p of t. We start by dividing the time interval of interest into n subintervals with endpoints t1, t2, t3, tn plus 1, as shown in this diagram. The starting point of the trajectory, p of t1, is known, so we can initialize that value. Then we calculate values for p of ti for I equal 2, 3, 4, up to n minus 1, using the computational equation p of ti plus 1 equals p of ti plus v of ti times dt. That is, the position at the end of the ith subinterval equals the position at the start of the subinterval plus the distance traveled during the subinterval, which is given by v of ti times dt. Now we have values for p of t1, p of t2, p of t3, up to p of tn plus 1, and we can graph them by plotting the points and connecting them with straight lines to get a piecewise linear graph. This method is known as Euler's method for computing solutions to differential equations, and was first noted by Leonhard Euler, a very famous Swiss mathematician, in the 1700s. Now we want to automate this method, and write a MATLAB program to perform the computations. MATLAB is a programming language written for engineers many years ago, and while many fancy extensions have been added, none of which we'll use, the base language has remained the same and is simple and intuitive. Still, some things may take some getting used to if you are new to programming, so let's take a brief tour of some of the language features. You can use MATLAB like a calculator to evaluate expressions, and it has built-in functions like those you find on a handheld engineering calculator. And it has variables for storing the results of calculations. Here we're looking at what purports to be the MATLAB command window, and the right arrow is the command prompt, and we'll type in some commands and see what they do. You can evaluate the expression 3 plus sine 1 and store it in the variable x by typing in the command x equals 3 plus sine 1 after the command prompt. MATLAB responds by evaluating the expression and printing the value, and also storing the value in the variable x. If you follow the command with a semicolon, the printing will be suppressed. Variables can be used to store one-dimensional arrays or lists. An array of numbers will be created and stored in the variable y by the command y equals left bracket 10 space 1.3 space 0 space minus 18 right bracket. Then you can access the elements of the array as shown. For example, y of 2 will print out the second element, and you can assign a new value to the second element of the array by the command y of 2 equals 3. MATLAB responds by printing the value of the array with all the elements, and you'll see that the second element is now 3. The built-in zeros function creates an array initialized to zeros. For example, the command y equals zeros, left paren 1, comma 4, right paren, creates an array of 4 zeros as shown. Also, an array of consecutive integers from 1 to n is created by the syntax, and this is unique to MATLAB, of 1 colon n. So the command y equals 1 colon 5 creates the array shown. We'll use an array in the program that's coming to store the start times of the subintervals. This will be the t array, and the elements will have the values shown. That is, the first element will have the time t1, which is usually 0. The second element will have the time t2, which is t1 plus dt. The third element will have the value t3, which is t2 plus dt, and so on. We'll also store the computed values of the position function in an array named p. The first element of the array will have the value p of t1. The second element will have the value p of t2, and so on. MATLAB commands in a program are executed one after another going down the page, with a for loop being used to execute a set of commands multiple times. The for loop begins with a for command, which consists of a for, followed by an index variable, followed by an equal sign, followed by a list of values, the for list. When the for loop is executed, the index variable is assigned the first value in the for list, and the statements between the for command and the matching in command are executed. Then the index variable is assigned the second value in the for list, and the statements are executed again, and so on, so that the statements between the for and the in command are executed a total of n times, where n is the number of elements in the for list. If you type in a for loop following a command prompt, it won't begin execution until the matching end is entered, and then the for loop will execute. For the example shown, each time through the loop, the value of the index variable is added to the sum variable, and since there's no semicolon at the end of the statement, the sum is printed. Thus, the command sum equals sum plus I command is executed 3 times, and the value printed 3 times as shown. Now we're ready to look at the program itself. It begins with the command n equals 2, where n is the number of subintervals. The second command is dt equals 5. dt is the length of each subinterval. We can, if we want, initialize the p and t arrays. Here we initialize p to an array of n plus 1 zeros, and we initialize t to an array of n plus 1 zeros. Now we initialize the first value of the p array to 500, which is the starting position of the apple hanging in the tree. And we initialize the first element of the t array, the time of t1, which is 0. Now we come to the for loop to do some computing. The index variable is I, and the for list consists of the consecutive integers from 1 to n, and since n is 2, the for list has two elements, 1 and 2. The next command computes the start time at the I plus first subinterval, which equals the start time at the ith subinterval plus dt. The next command computes the velocity at the start of the ith subinterval, which is minus 10 times the time at the start of the ith subinterval. The final command in the for loop computes the position at the start of the I plus first subinterval, which equals the position at the start of the ith subinterval plus the distance traveled during the ith subinterval, which is the velocity at the start of the ith subinterval times dt. When the loop completes, the plot command displays the graph. In the next video, we'll go online and enter, debug, and execute this program. The assignments are, number 1, calculate by hand the approximate trajectory for a falling apple for 2 seconds from a height of 10 meters, dividing the time interval of 0 to 2 seconds into 4 subintervals, each of length a half second. Graph the solution. The second assignment is to get MATLAB, FreeMat, or Octave running on your computer. We'll enter a MATLAB program in the next video, and you should follow along. MATLAB is used to refer to both the programming language and the application that executes MATLAB programs on a computer. The official MATLAB application is available to students for a small $50 fee. However, if you're not a student, perfectly good free clones of the MATLAB application, my favorites are Octave and FreeMat, are available to all for free, and these applications execute the exact same MATLAB programs as the official MATLAB application does, and are for our purposes equivalent to it. Links to the sites where MATLAB, Octave, and FreeMat can be obtained are in the description below. The first thing we'll do in the next video is go through the steps necessary to get Octave running on a PC.
This is how we do it. South Central, like nobody does. This is